Hello dear students, myself Assistant Professor Partha Mistry from Mahatma Gandhi Institute of Technical Education and Research Center Navsari. Today we discuss our chapter number 1 topic. The topic name is Thevenin Theorem. In last video we discussed about the example number 3 and example number 4 of Thevenin Theorem. Today in this video we discuss more to example with new configuration and we discuss more to examples, example number 5 and example number 6. So let us start. Here is the flow of content of our video. First of all, again we recall the statement of Thevenin's theorem. Then after we go for the example number 5, then example number 6, and finally we discuss about the GTO questions which will be repeatedly asked. So first of all we discuss the statement of Thevenin's theorem. Here is the statement of Thevenin's theorem. It states that any linear active network with output terminal can be replaced by a single voltage source VTH in series with a single impedance ZTH, where VTH is known as Thevenin's equivalent open circuit voltage and ZTH is known as Thevenin's equivalent impedance. So any network can be replaced with equivalent Thevenin's open circuit voltage, or we can say Thevenin voltage VTH, and the equivalent impedance of that particular network noted by ZTH. So if we find both the values, we can easily develop the Thevenin's equivalent circuit and we calculate the load current. So equation for the load current IL, that is equals to VTH divided by ZTH plus Z load, or we can say impedance offered by the load. So this is the statement of Thevenin's theorem. So here graphical representation is given. Here the network E is provided over here. From the terminal AB, the load is connected. So entire network A can be replaced by Thevenin's equivalent voltage source and its equivalent impedance, that is ZTH, and whatever the load is connected between A and B is connected over here. So entire network A can be replaced by equivalent Thevenin voltage and equivalent Thevenin impedance, that is ZTH. So today we discuss the example number 5. So let's start the example number 5. The question is that the network of following figure contains a dependent source. Find the Thevenin's equivalent network across the terminals A and B. So we have to find the Thevenin equivalent circuit across AB. Here we can clearly see that one active source, or we can say one independent source, that is 100 volt, is given, and one dependent source, or we can say one dependent current source is given, that is also given over here. So we have to develop the Thevenin circuit across the terminals A and B. So here one independent source and one dependent source is given. So for the calculation of ZTH, we consider the step number 2, that is ZTH equals to VTH upon ISC. So we have to find out the VTH, then we go for the short circuit current ISC, because here dependent source is given. So let us start the example. The Thevenin's equivalent voltage is equal to V1. So whatever the voltage we achieve between A and B, so let us consider that is V1, or we can say V1 equals to VTH. Okay, so to find V1 we write the Kirchhoff voltage law equation. So if we apply Kirchhoff voltage law in the figure 1, so we get the value like this: 20 multiplied by V1 divided by 100 bracket over minus 2 plus, that is plus 100, which is equals to V1. So what is the value of V1? So V1 equals to 100 plus 20 multiplied by V1 divided by 100, or we can say 20, that is our resistance, and V1 divided by 100, that is current flowing from this resistor. So we can write 20 multiplied by V1 divided by 100 plus 100, which is equals to V1. So by simplify all the things, we get 4 over 5 V1 equals to 100, V1 equals to 500 divided by 4, and we get the value of V1, that is 125 volt. So initially in first step we calculate the V1. So simply we apply the Kirchhoff voltage law in this figure and we get the value of V1. So as discussed earlier, in next step we calculate the value of ZTH. Okay. So short circuit the terminals AB. So whatever the terminals we give notation, that is AB, which will be sorted, and hence V1 equals to 0. Why V1 0? Because here the dependent source is given, dependent current source, and their dependency is on this side where V1 is plotted. So here V1 is 0. So this source also becomes 0 because the dependency of this source is on V1. So in this case V1 will be 0. So this dependent source will also be 0. So the current of the dependent source become 0. So now the circuit is become like this. We start the V1 over here. So due to that the dependent source is also 0 because active source becomes 0. So ISC becomes V upon R. V tends to 100 volt, R tends to 20. So 5 ampere we get. We have both the values VTH and ISC. So we easily calculate the ZTH. So ZTH equals to VTH upon ISC, that is equals to 125 divided by 5. So 25 ohm. So ZTH we achieved, that is 25 ohm. So our answer is very near. So we have the value of VTH, we have the value of ZTH, so we can easily build the Thevenin equivalent circuit. And the question is, we have to build the Thevenin equivalent circuit between terminal A and B. So Thevenin equivalent circuit becomes like this. So VTH equals to 125 volt and ZH equals to 25 ohm. So between terminal AB, we easily plot both the values with proper notation, and this is our final answer. So hence we have to develop the Thevenin's equivalent circuit between terminals A and B. Next we discuss the example number 6. So the question for the example number 6 is, obtain the Thevenin's equivalent network for a given network of following figure. So here one figure is there and we have to develop the Thevenin equivalent circuit. So first of all find the how many active source or how many independent source and how many dependent source given in the figure. So we can clearly see over here that one dependent source is given, voltage dependent voltage source. Here one independent source is given, that is 150 volt, and here also one independent source is given, that is 5 ampere. So initially what will be our first step? So initially we have to find the value of VTH by applying Kirchhoff current law at node X. Okay, so we have to apply the Kirchhoff current law over here. So what is the value of current at node X? So sum of current entering equals to sum of current outgoing. So in this phenomena, we clearly understood that all the currents are comes from the outside. So the value of current entering is first of all Vx minus 150 minus Vx by 3, because all three are voltage value. So major voltage value we take over here, that is Vx, which will be already given in the figure. So what is the value of voltage, value of current from this loop towards the Vx? So total Vx minus the actual voltage will be given over, that is 150, and the dependent source, that is Vx divided by 3. So all the values are given over here and we both are deducted from Vx. So Vx minus 150 minus Vx by 3 whole divided by the resistance offered by that branch. So simple, Vx minus 150 minus Vx by 3 whole divided by 10. This is nothing but simply Ohm's law, I equals to V upon R. Okay, so here we have write the all the current equation because we apply KCL over here. So for the first loop, again we repeat Vx minus 150 minus Vx by 3 upon 10. This branch is also concerned resistance offered by, that is 15 ohm. So the Vx divided by 15, and in this direction the current is flowing, that is 5 ampere. So plus 5 equals to 0. So in this case we simplify the equation. So after taking LCM we get the value of Vx. So 3Vx minus 450 minus Vx divided by 30 plus Vx divided by 15 plus 5 equals to 0. Further simplifying, we get 3Vx minus 450 minus Vx plus twice Vx plus 150 equals to 0. So 4Vx equals to 300 and Vx equals to 75 volt. So we have the value of Vx, that is 75 volt. Our step number 2 is calculation of RTh, or we can say ZTh. So again apply Kirchhoff current law at node Vx. So at node Vx we apply Kirchhoff's current law and we short the branch. So over here we short the branch. So the configuration becomes now different. So applying Kirchhoff current law at Vx, we get the value, that is Vx divided by 30. So for the first branch, Vx divided by 30, then plus 5. So for this branch, plus 5 plus Vx divided by 15. So for this branch, plus Vx divided by 15 plus Vx minus 150 minus Vx by 3 divided by 10. This is quite same as the previous case. So by short circuiting the AB, we just add Vx by 30. So by simplification, taking the LCM, we get the value of Vx. So Vx divided by 30 plus Vx divided by 15 plus Vx divided by 10 minus Vx divided by 30 equals to 15 minus 5 equals to 10. By further simplification, we get the value of Vx. So Vx equals to 60 volt we get. So we have the both the values. So we easily find the value of IS, that is Vx divided by 30. So which is equals to 60 divided by 30 ohm. So we get the value of short circuit current ISC, that is 2 ampere. So we get the value of ISC, that is 2 ampere. So we have the value of VTH, we have the value of ISC. So we can easily calculate the RTH, or we can say the ZTH. So VTH upon ISC, VTH tends to 75 volt, ISC tends to 2 ampere. So we get the value of 37.5 ohm. So RTH we will get 37.5 ohm. So we have both the values. So we easily build up the Thevenin circuit as per the previous example also. So VTH is 75 volt, RTH, that is 37.5 ohm between terminals A and B, we can easily put. So this is the Thevenin's equivalent circuit between terminals A and B. So this is all about the Thevenin's theorem, and our GTU question is that which will be repeatedly asked, that is state and explain Thevenin's theorem. And this question is asked in your GTU exam, that is December 2018 and December 2009 for the 3 marks. In second manner, the question arises that state and explain in brief Thevenin's theorem, GTU May 2012 for 7 marks. The numerical is asked. Question is that the network of following figure contains a dependent source. Find the Thevenin's equivalent network across the terminals A and B. GTU May 2018 for 7 marks. So friends, there is a probability of question in which the dependent source is given. So that kind of numericals ask more in your GTU example in Thevenin's theorem. Another question is that obtain the Thevenin's equivalent resistance of following figure to the left of terminals AB. GTU December 2019 for 7 marks. So in all the case we have to obtain the Thevenin's equivalent circuit, and it is very easy if we know all the fundamentals principle, and if we know in which manner we have to calculate the value of ZTH. We just find out the two values and we build the Thevenin equivalent circuit. First of all VTH, and second one is ZTH. Thank you.